Um, Hi everyone, I am Anna Saranti and I will talk about explainable artificial intelligence. I want to personally thank Aaron who invited me for this workshop. I hope that everybody already has a basic knowledge of what neural networks do, what neural networks are. I'm really happy that I saw that tomorrow you will have an introduction in graph neural networks, which I will briefly also talk about a bit later. I am currently studying in Austria, in Europe. My supervisor is Professor Andreas Holzinger. And yeah, let's get started. The outline of my presentation today will be as follows. I will concentrate on one particular very important explainable AI method, which is called layer-wise relevance propagation, so that we all get in the same page and learn the basics of what a very important explainable AI method does. I will compare it to older ones and not so, let's say, sophisticated ones. I will teach everyone and share my knowledge about what is possible to do with bigger data sets, because I hope that I'm talking to a bigger audience that encompasses also students, data scientists, and people perhaps from the industry, which I also worked on. I will also show you how explainable AI can help you see what's happening into a neural network of different architectures. There are neural networks that process images, neural networks that process text, others process graphs, and how can you change your data set according to explainable AI methods. And then, of course, I will jump into stuff that we are doing now currently in the lab in collaboration with different universities, mostly in Germany, the University of Göttingen and the University of Bamberg. And of course, I will make sure that I will answer all your questions in the end. So we know that neural networks help us to do several tasks, and the most basic one is a binary classification task. In the Medical University of Graz, for example, we do have lots of images of cancerous and precancerous cells and tissues, and doctors there and people that work there would like to see if neural networks can accomplish classification tasks. And on the one hand, we will see that those images contain cells and tissues. Some of them are more concentrated, some of them are not so concentrated. And we did experiments where we inputted those images into neural networks, and they also learn if an image represents a cancerous part or a non-cancerous part. After we used the neural network reached a good performance and can tell us with a good, let's say, metric, like mutual information, for example, what is cancerous and what is non-cancerous, we go back and ask the neural network, why did you say that? Why do you think that this input is cancerous or not cancerous? And one of the simplest and earliest methods encompass heat maps, where an explainable AI method is applied after the training process is done and shows us which parts of the input image played the more decisive role towards saying cancer or non-cancer. Here you have an example where this input shows that this part of the issue where the cells are not so concentrated helped the decision, and the other part where the cells are much more concentrated played a role. And there are also white spaces in between that show that they didn't play a role in the classification at all. So this is the main task of any explainable AI method, is to show us what was the decision, why it was taken, and which parts of the input did play the role or not. So what is a good heat map? That's the question. Since we decided that we use explainable AI to present the important and non-important parts of the heat map, what is a good heat map? Because there are many methods that we can compute a heat map. We can use sensitivity analysis, and we can say that the sensitivity of a pixel is the norm over all partial derivatives. This represents how much a small change in the pixel affects the prediction output of the neural network, but the direction of the change is lost because we use the norm there. And it also puts a restriction in the architecture of the neural network that we can use with this method. So we need locally differentiable neurons to do that. We cannot do that in any neural network architecture. And one also way to, in a fictive example, to compare what the two methods do and why one we consider it to be more important than the other is one fictional example when we separate blue points from green points, and we see that this line here is the decision boundary, and LRP finds the root point on the decision boundary and finds the direction towards the other class. And shows us exactly in what direction we have to do to jump from the one class to another, to put it in a very, very general way. And the Taylor approximation with respect to the root point of the decision boundary can help us to see completely different heat maps with completely different qualities. Here in this example, for example, you do have an image with people on motorcycles, and in the same neural network, the sensitivity analysis shows us back that this is the heat map, whereas LRP shows us this heat map. This heat map has only a color map from a range of white to red, but this heat map has also blue parts, actually. That shows that the important parts, and they are much more detailed oriented in the LRP case, speak towards a prediction and help us classify something as being cancerous, or this image as containing motorcycles, for example. But shadows, for whatever reason, this neural network has decided from the training process that they speak against it. That means that probably the images of the other class do contain a lot of shadows, and those shadows in this image did irritate the neural network a little bit in its decision. So we do have in LRP evidence for the predicted class, and we have evidence against the predicted class. This is something that we don't usually see in other heat mapping methods. This is why it's very important. Also, one example for visual comparison. Yes, heat maps from sensitivity analysis and other methods do show us that the bird's body is important for the classification, but they didn't concentrate on colors, lines, and the like, and its separation from its surroundings. Okay, so we did understood the whole pipeline. We gather our data, we train a neural network, and then we apply an explainable AI method, which is also a software, and we see for each input that interests us, we see a corresponding heat map. But we are data scientists, we deal with big data in the meantime, so we cannot pass and see every possible heat map and check, does our neural network do the right thing or not? So people did came across situations where very important and very performant convolutional neural networks that also won prizes were trained in the Pascal VOC 2007 dataset. They did have a good performance, but they based the decision on some artifact, and humans do have an expectation of what a neural network should base its decision on. And people from the Technical University of Berlin showed that this dataset has actually an artifact. So each image that contained a horse had a tag on the left down side. And they tried to see with their LRP heat maps what is going to happen if they put this tag and copy paste this tag in an image of a car. The neural network said, this is a horse. So it's based on its decision in something that humans didn't want it and think that it's cheating. They found a name for that. They called it Clever Hans prediction. So it's just a correlation. And even if you have a data set that participates and it's used in something that's big, like a Kaggle competition, for example, it also is faulty. So data sets do have quality problems. Software is buggy, and explainable AI is also a piece of software, but can help us detect all those things. This can be also semi-automated with a method which is called semi-automated spectral relevance analysis. We do take all the heat maps of all our images, and we can see that if we cluster them, then the concentrations of red parts and blue parts, positive relevance and negative relevance, they may be completely different for different groups of heat maps. And then we can come to a conclusion that the ones where the heat maps are on the left downside is a tag, the ones where the horse is in the middle of the image, and we expect the classification to be correct because the horse is indeed there, that they will have, they will be in completely different classes, and we can see the large eigengaps between their eigenvalues, and we can say, oh, let's see what criteria did help us for the classification here and what there. Maybe the neural network bases its decision in some kind of artifact, which is hopefully an outlier and not the central reason. We can, by that, improve both the model and the data set in the end. And let's see what LRP does in, for example, recurrent neural networks that process text, and how it's compared with sensitivity analysis. We here trained LSTM in a sentiment classification task. I think that was the Stanford SST datasets, where it contains lots of textual data of people that criticized movies from, and they had 5 classes from very negative, I think neutral, and then positive to very positive. And those are examples of sentences that contain very negative sentiment. And the LSTM, the trained neural network, predicted it correctly as being very negative. The sensitivity analysis shows us that, for example, neither not, stupid, tedious did play a higher role for the classification, whereas, for example, picture or star didn't play, or as off is not important, is irrelevant. But LRP goes beyond that and says, okay, waste and neither played a role in negative connotation, but funny is something that actually has a positive sentiment, and it, of course, the neural network in the end classified this correctly, but we do come to an idea, okay, what will happen in the prediction if I remove funny, if I remove originality, if I remove some of the words that have a positive flair on them. And what they observe is that if they sort all the words according to positive relevance, when we have a correct classification, and then they start removing the most positive relevance and the second positive relevant in a sequence, then the prediction performance of the neural network will drop monotonically and will drop really, really fast. Whereas if they use the sensitivity analysis to do the same thing, then the drop exists, but it isn't that intense, it isn't that hard. The opposite and corresponding effects happens when you have a misclassification and you remove the most important words, the ones with increasing relevance sorted. And for me, this is a forefront for counterfactual explanations, which I will talk a little bit later, where the idea is to ask what will happen if I remove parts of the input. How will this affect the performance of the model? Would that improve the model, or would it worsen the model? How will it inform the performance of this particular prediction for this one particular data point? Usually what we teach in the Technical University of Graz and Vienna, actually for people to get to know LRP, students and me myself also to get to know LRP, we start with a simple fully connected neural network that supposedly processes an input image in the old good fashioned way, before convolutional neural networks were invented for a classification task. The neural network computes okay, good. Sorry for this pause, but I was informed that that the recording has stopped for a while. Okay, good. And what is important also to see in this example is that we do have heat maps for correctly classified elements, and we also have heat maps of misclassified elements. The heat maps of misclassified elements don't contain much information. We say that they don't make sense somehow, and it's part of research to find out what kind of information is contained in heat maps of misclassified elements and of heat maps of non-efficient and not good and overly trained neural networks that don't have a good performance, if there's something that we can learn from them or not. And we see, for example, that heat maps pick up the parts of the image that differentiate between two or more classes. This is an example of heat maps of a neural network that was trained on the MNIST datasets. And we can see here that the center of the image that contains a 0 plays a decisive role, because this is something that's unique in comparison to other classes. So classification and discrimination is helped by the features that are unique for all the images in a particular class. And this is hopefully picked up by the explainable AI method that we have chosen. The neural network training procedure and the pipeline containing explainable AI and LRP is feed-forward. And although the neural network is trained by backpropagation of the error of its prediction with the training data, what we still call it feed-forward, even if we have feed-forward propagation and backpropagation. And after this has finished, and after hopefully we have a convergence of the performance, and layer-wise relevance propagation can be applied after the end of the training procedure. And it only needs one backward pass if you're talking about fully connected neural networks. And most of the convolutional neural networks, I will not talk about the ResNet that has also backward connections in it, maybe in the question time. And for the graph neural networks case, one must have multiple propagation passes. But please do not confuse this with neural network training with forwards and back propagation. The back propagation of LRP is done once after the training is done. And the computational flow of deep Taylor decomposition, which is the mathematical basis of LRP, takes the output, and we can imagine this as computing the relevance going backwards from the output to the uppermost layer and the layer before it and the layer before it until it reaches the input and computes relevance values for each pixel, for each word, for each element of the graph. So each element of the input will have a particular value, which will then visualize with Matplotlib or whatever other method we would use. This is also a depiction of that. And we can also see here a fictive example where a neural network has discriminated between images that contain the cat and the ones that don't contain the cat. And hopefully the LRP would predict that this image contains a cat and will concentrate on the ears of the cat and the nose of the cat to say, this is a cat. I classify this as cat, as a cat image. The relevance propagation is based mathematically on the Taylor expander that we've learned in school. We want to decompose any input with a known input f of a, which a is very near to x, and hopefully we will find a root point to do this effectively, because if we do that, we can decompose the relevance on the uppermost layer with relevances of the previous layers, and then do this game again and again and again and again. It would be very difficult to find a root point to expand the output of the neural network to do this process. And also one example of how this might that's again a fictive example of the research of the people at the TU Berlin. They say, okay, we have a neural network. This is the input. This image contains a building. But if we blur a little bit the image, then the neural network doesn't recognize that there's a building. So because it doesn't probably differentiate it from the background. So if this root point is classified as 0, not containing the building, and the input as 1, containing the building, and we take the gradient of the f, the function f that is computed by the neural network with respect to this root point and the difference of those images, then we can have a heat map that picks up the edges and the parts of the building that were decisive to classify this image as containing the building. So the whole process of this explainable AI method redistributes the neural network output prediction onto the input variables layer by layer from the upper to the lower. The difficult thing is to find a neighboring point for which the function is set to 0. And a good root point is the one that removes elements from the data point that cause f of x to be positive in an object detection scheme, leading us back to and connecting us back to perturbance analysis, leading us to counterfactual explanations. And we are looking for a similar image where the object is not recognizable from the classifier, hence this output. Sometimes this image doesn't make any visual sense, and it can be found with optimization methods. But the tool of the Python tool that implements LRP, which can be found in GitHub, does that in a quite effective way for most of the cases. Properties of layer-wise relevance propagation. One of the most important is the conservations. There are others like positivity. Relevances of a particular layer equal the sum of the relevances in the previous layer. This can help us build also test cases, which is something that we did in our paper of practical tutorial for explainable AI with Professor Natalia Rodriguez, which is out. This can help us to check our results and build also test cases to have a minimal check that our numerical computations are quite correct. This is one of the examples that we teach at the university, where I ask my students to just take a pencil and paper and have a very, very small neural network. I will not go into that, but I will leave that in the slides. There are also YouTube videos where I explain that to the students. And one can sit down and set fictive numbers for the input, some corresponding numbers for the weights and biases, and put the output, do some fictive forward pass, and then can compute from the output what are the relevances of the networks in the middle layer, and what are the relevances of the input, and also check that the sum of the relevances in this layer equal the sum of the relevances here and the sum of the relevances here. Make a test case, have quality in what you are computing or what you are programming, and also play around and see all those possible combinations, juxtapositions of different possible values in the weights. See what happens if you select random weights. See what happens if you have a high number here and a high weight here and high weights here in between. How does that affect the output prediction, and how does that affect the relevance of this particular input with respect and in comparison with relevances of those two that probably have a lower value. And those mathematical equations can help you to and make your computer see and for yourself. Okay. Let's wrap up. What are the benefits of LRP? We have more interpretable heat maps. They make more sense, quote unquote. We have positive and negative relevance, which is a very important concept. We discover artifacts in big data sets without seeing every heat map from every possible data point. We have action. That means we think towards what this, what if that wasn't there, what if something, towards counterfactual explanations. And all those principles can be applied to new neural network architectures like graphical neural networks with support of quality management, because we never forget that what we compute can also contain bugs because it's software. I will talk a little bit of explainable AI on graph neural networks without diving into graph neural networks. Before I get into that, and speak a little bit more in detail what we are doing in the lab and what direction we want to go. Yes, we do explain the neural network's decision process, but even humans, when confronted with an image like that containing both a cat and a dog, would be irritated, and it would be questionable in what class this image belongs. So if you go around and ask people, some of them will say that the dog is more prevalent because it's in front. Other ones would say that the cat is played the bigger role for them because it is in the bigger part of the image. The dog is on the left downward side. So you will have different people will classify this differently. LRP also helps us here to decide and see that if the neural network predicts this image as containing a cat and classify this as cat, then those parts played a positive role and those parts of the dog played a negative role, and the neural network is not so sure. And the opposite exactly happens if it classifies something as a dog. So the idea that we would have is what would happen if we remove some parts. And what will happen if we are not dealing with heat maps of images, but heat maps on graphs? What will happen if we had not graphs, we didn't have images as an input, but we did have graphs? And how would the heat maps on graph would look like? What would be the parts that would be highlighted? Probably there will be subgraphs, probably there will be walks. Here I just show you an image of heat maps of images, but you can imagine theoretically what would a heat map look like from a neural network that is trained not on the images, but on graphs of the cells. GNN explainer is one of the first methods that were invented and computes the important subgraph of the computational graph of the input graph. It uses an optimization algorithm where it iteratively tries to find the substructure that maximizes the mutual information between this graph and the prediction score. So as we previously said, we assume that for a convolutional neural network, parts of the image played a role and parts didn't or played a negative role. Similarly, explainable AI methods of graph neural networks that currently are developing, they take on those kind of assumptions and say, probably it's a particular node, or probably it's an edge, or it's a connection between lots of edges, or it's a subgraph, a motif. And this is what I'm trying to find. I'm trying to find which of those produces the high mutual information between the same prediction and this one, and forgetting the other ones. And I'm trying with optimization methods to get into that point. Okay, good. X of S is the subset of features of node or particular subgraph that I'm searching for. Epsilon is the probability distribution of the label. And this is a very, very time-consuming method to compute a subgraph and also parts of the features of the nodes in the graph. We did use this in the lab, first with synthetic data, and we showed with a very, very simple example that I'm presenting here for people that want to know about this, that if we have a set of 1,000 graphs with the same topology, and half of the graphs do have a connection between node 4 and 5 with features that were sampled by a Gaussian distribution with mean 0 and deviation 0.1, then those node features in the other class are slightly different with a different mean value and the same span of values. Then the graph classification is giving us a good enough performance, and the GNN explainer does show that the part that differentiated those two classes of graphs. The one that was decisive is the one that is also shown here in red, and that was an easy way to also check that the GNN explainer gives us plausible results with a very, very, very simple first data set. The PGM explainer goes back into the perturbation analysis and counterfactual explanations. One can perturb the input to uncover dependencies and learn also a Bayesian network from the generated data. Of course, we do play around with the graph. Then we gather a lot of graphs, and then we can do structure and parameter learning into the Bayesian network, and we can see on which features, probability distributions a particular node's prediction is based on. In the end, we do get a Bayesian network, directed acyclic graph of how the distributions of the features of each node in the graph played a role for the prediction of, I think, it's the prediction of a epsilon, sorry. But we do that in a way that it's either an optimization method in comparison with a metric, and we don't have the human factor in it. So we do estimate the probability that a particular node epsilon has the predicted role, given the values, as I said before, of the features of other nodes. But all those take into account and think that the neural network did everything correct and has a very good and high performance, and they do produce plausible results and good results if the classification performance is good, if the classification is in accordance with the label that we were given, it's in accordance with the ground truth. But what will happen if we do have a bad performing neural network? What will happen if the prediction isn't good? One is not sure because, as we said before, we do have the cat and the dog on the same image. What we can do there when the neural network is irritated? And our approach here in the human-centered AI lab is that we use the graph neural network and the Factuals UI platform, where people can load up graphs and graph data sets, whole data sets of graphs. Each node can contain a lot of different features, but the same means that an image has 3 values at least. So the RGB, a particular node possibly extracted by a histopathological image, can contain much more than 3 features, like the sizes, the colors, convexity, the perimeter size, and so on. And we can also see the numbers and the values of those features, but the users are also encouraged to try out additions, deletions of nodes and edges and features, and they will see how the relevance of LRP and other explainable AI methods are. And explainable AI method can also tell them that a particular node is very important, and they can delete this node and see how and if the performance of the neural network is hopefully dropping or not. But they also can see heat maps or heat graphs, as we call them in the lab, where the heat graph will tell them this node is important, but the human, the doctor, I don't believe that. My knowledge is different. Maybe your neural network is not performing perfectly. Maybe your heat mapping method is not the best. It contains bugs in it. The data set is not that good. So we do think that good performance provides good explanation, but we want to provide the international community with a tool that brings also human knowledge into that, so that we don't blindly trust even explainable AI results and even neural networks results. We can incorporate human domain knowledge and get out of those situations where heat maps make sense, we don't have enough performance, and out a lot of things. Like one of the most simple ones would be predict and retrain, and the difference would be that sorry about that. Okay, the difference between predict and retrain would be that if a user change part of its data sets and says, okay, I'm going to change those 3 graphs and I'm going to add things and I'm going to remove things, I will check what the prediction is, but the prediction does just change for all those, only those 3, the other 3 did remain the same. And of course, the relevances will be then completely different. So if I remove an important node, then I expect that the prediction will be different for this graph, and also the relevance distributions will be different also for this graph. The retrain process, in the retrain process, we will change parts of your data set or all the data set. We will do a full retrain of the graph neural network. We will have new predictions and new relevances that we will check, and then this game will continue on and on and on. And we are very, very excited and very happy to see the, what the insights of the doctors will be, how will they react on the explainable AI results. And we will measure that in our lab, in our causability lab, and we will measure the degree of their understanding on what basis the graph neural network takes its decisions, and on the degree on that the explainable AI methods that we provide them shows them the causal connections between the input and the output prediction. This is how, for example, would our platform look like. We do have a very nice data set that contains proteins and looks almost like that. We will have a very nice sorting of nodes according to relevance and edges according to relevance. People will select the nodes in their neighborhoods to see roughly what happens. They will have the ability to see what the features are, what kind of proteins do we have, and then they will decide what kind of modifications they will do, and the process will go on and on and on. I'm coming to the end of my talk. This is the literature of the main layer-wise relevance propagation paper. All the math, or almost all the math, are there. It's from 2017. The differences with sensitivity analysis optically are very important. Just look at those papers and just only look at the differences of the images. This gives everyone a very good picture of how important is the quality of explanations for further decisions and further insights. The whole dataset analysis is in the following paper, came a little bit later in 2019. The paper on perturbation analysis, the forefront of counterfactual explanations, came in 2017. And 3 of the explanation methods are here: GNN explainer, PGM explainer, and GNN LRP from Thomas Schnacke from 2020 are here. There are many, many more to come. There are many, many more that play around with perturbations of the graph, that try out motif explanations. They also bring concepts inside. The software for explainable AI methods for graph neural networks is not yet so evolved, but it's something that we as part of the research community have to promote and have to use so that it gets better with time. So I'm happy to hear your questions, and thank you very much.
Yes, thank you so much for the insightful talk, Anna. So participants, if you have any question, please go ahead with the questions. You can unmute your mic and speak out, or else you can send your question in the chat. Yes, if anybody is having any doubt, any questions, please. You can also post your question in the chat box.
Hi, Anna, it's a nice talk. This is really a, very important topic nowadays, that is explainable AI. Now, just since you have discussed about GNN and all, so I would like to talk something related to that. Basically, whenever you have a very complex network, and if you want to see how your model is basically working, you have to go for a visualization. Am I right? You have to go for a
Most of the
visualization,
time, yes.
and there will be a kind of a series of visualization. There will be a series of visualizations to show the individual steps, how actually the machine is learning, or my model is basically learning. So in that case, the issue is that, like, when you go for a very large network, possibly it would be very difficult to visualize it very nicely, because normally real life networks are very, very large, very complex. And in that case, if you have to go for such kind of series of visualizations of the graph, that how actually the transformation is happening or how the prediction is correct, in that case, possibly it would be very difficult to render those things. So in such case, how are we going to handle such situation?
Okay. First of all, don't panic, because everybody has the same problem, the one that you actually expressed. Okay. So I'm just going to go back and tell you that I don't have it open, but I can open it. This method, for example, GNN LRP, is extremely difficult for a lot of people to understand. Okay. And what they do, maybe I can open this, what they do to show the heat maps is actually very difficult also to visualize. Their assumption is that, as we say for images, the pixels are important. They are going to say which walks of the graph are important. So what does that mean? That they say, I'm not going to concentrate on one node or one edge, okay, individually, because a particular node or a particular edge might be important just because it's connected with somebody else. So what is the result of that? They return for a graph that can contain, let's say, 10 nodes and 20 possible paths of 3 nodes. They return for every possible path of 3 nodes a relevance. And you can the resulting heat graphs, blue, red, gray, everything. And they did the following. I don't know. GNN LRP. I will show this right now. I hope that can be shown here. These are their input graphs, right? Look how difficult are their explanation to present. They have on the same edge quite different relevance values. One can, of course, always compute the mean, but that's not also so that correct. And you see how difficult that is? This is the visualization burden is much, much higher. What I did in a personal project, I used bokeh, and I will also show you that here. This is one of the Python visualization libraries that I recommend. And I will show you, apart from another presentations that I did last month in Canada, which was concentrated on GNN. This presentation wasn't, and I explicitly saw that you will get the knowledge for GNNs. And I can show you how I solved the problem that you're referring to. I used bokeh to have HTML output, okay? And you can see that I can click on the legend and I can say, please give me the relevance of this graph. This is 0.1. Please give me the relevance only of this. And I can say, I want to see only, so to speak, only those 3. So I can, so to speak, trigger and activate only the relevance of one path and the other path and the other path, and then have a visual of all of them together, which is not perfect. It's never going to be perfect. So this is the solution that I found out. But I totally agree that this is a problem. So one has to search for better visualization libraries. One can find them, and one can find, this is my personal solution, and this is the solution of Thomas Schnacke, for example. He uses Matplotlib, and he plots relevances around the edges to find the way.
Thank you, Anand. It's great. Like you have given a lot
We
of
all
good
keep
comments.
up the good work. Every one of us tries to find something that fits to the problem at hand.
Yeah. Thank you, Anna. Thank you so much. Thank you for your nice explanation.